So if you missed class or you just want to review this part of the lesson, this is the activity where we were kind of working with both counts and proportions. Now, admittedly, your notes primarily focused on the binomial distribution. So we were kind of refreshing what we had studied the previous semester, where we had mean as n times p, and some of you were noting, this includes some notes that you guys shared, that how distributions can be skewed and how to calculate standard deviation. So that's from the notes, all right? And there's a video that goes with that. Here, we went ahead in class, and I had you flip a coin 40 times. And we used those notes. You can see I actually captured it straight out of the notes. The formula for the mean was n times p. The formula for standard deviation is square root of n times p times 1 minus p. So in this case, p is 0.5 because the probability of getting heads, we're like x is the number of heads, then it's a binomial random variable, and this is from not their lesson 5.4, not my lesson 5.4. And we calculated the mean, and how do we interpret it? On average, we expect to get 20 heads out of 40 flips, all right? Then we did the formula for standard deviation, and we found it was 3.16. And so how do we interpret it? The number of heads will typically vary from the mean of 20 by 3.16 heads. So then we had you toss a coin 40 times and record the number of heads. Now, they wanted you to do it 4 times, but I went with 2 because I have large enough classes. We don't need the extra. And then this is a distribution that one of the classes came up with. And you can see there's the mean is very close to 20, and it kind of looks like a normal distribution. Not exactly. Probably would have helped if I had you do it 4 times, but I'm like, we're probably fine. All right. So, by the way, this won't always look like a normal distribution. You really tend to need a lot before you start to get the shape really well. All right. So let's think of the sampling distribution as a normal distribution. Well, we had the mean calculation, and we had the standard deviation calculation. So we had everything we needed to go set up a staplet. See, there's the mean is 20, and the standard deviation is 3.16. And I asked you to calculate the probability of 25 or more heads. So if I was going to normal, 20 and 3.16, plot the distribution. Oh, and yeah. And then I say 25 or more heads to the right of the value, 25. And you can see there's the probability, 5.68. Okay, so with 25 heads out of 30, would we have convincing evidence that the coin is unfair? Well, we're kind of trying to introduce you to an idea that we're going to be doing later when we do hypothesis tests. And it's like, okay, there's a claim. In theory, the coin should be 50-50. So we should normally get 20. And by the way, this should be 40 here out of 40 because I changed the numbers. So if you see this video in a later year and you're like, oh, the handout looks different, it's because I fixed it. All right. If we had 25 heads, does that mean we have an unfair coin when we do 40 flips? Well, the thing is, we expect 25 or more heads about over 5% of the time. Anything over 5% is not considered unusual, so you don't go, things that would make you go, Of course, you haven't heard that song by CNC Music Factory. But anyways, so it doesn't make me go, I'm not amazed. So there's no reason for me to doubt that it's a fair coin. All right. Now we go ahead and we do some practice. And there again are the formulas. Those are the big things. And then if there are at least, so in my notes, at least for the binomial distribution, I wasn't real obvious that this is the opposite of the condition. So the good news is you probably want to go ahead and copy this down. But we'll get to them. They're actually the same conditions in the next lesson. So you can kind of wait till we get there too. But basically what this says is if there are at least 10 expected successes and 10 expected failures, we can use a normal distribution. So here we have an example. About 10% of the people in the US are left-handed. All right. By the way, that 10 does not have anything to do with that 10. It's just coincidence. Could have been 12%. Suppose we take a sample of 120 US residents and let X equal the number of residents who are left-handed. We need to calculate the mean and standard deviation and interpret the standard deviation. So the mean is n times p, n is 120, p is 0.10. So 120 times 0.10 is 12. The standard deviation is n times p times 1 minus p. So I do 120, 0.1, 0.9, and I get 3.29. So how do I interpret this? Well, the number of left-handed people in a sample of 120 people typically varies from the mean of 12 by 3.29. All right. And then can I use a normal? So this is true regardless of what distribution I use, because that is the mean and that is the standard deviation, whether I use a binomial or a normal distribution. Okay. But I did need the binomial to get the formulas to calculate them. All right. Can I use a normal distribution? So I have to check the large counts condition for that. N times P, I'm getting 12. 12 is greater than 10, so we're good. N times 1 minus P, we're getting 108, also greater than 10. So yeah, we can use the normal distribution. So now calculate the probability that 16 or more individuals in the sample are left-handed and show your work. So we're going to use the mean. And we're going to use a normal distribution with this mean and this standard deviation. So I would put 12 and 3.29 in the staplet. Plot my distribution, and we wanted the probability 16 or more. So to the right of 16, calculate your area, and you get 0.112. All right. So 0.112 or 11.2%. All right. Then interpret your answer from number 3. When taking a random sample of 120 residents, there is an 11.2% chance of getting 16 or more lefties. So that is part 1 of Is This a Fair Coin?